Hi everyone. In today's lecture, we will continue with the diode models. So in the last lecture, I discussed about the need for going for diode models, and one of the reasons we said that was when you have any circuit containing diodes, the analysis becomes extremely complicated if you use the exact diode equations. So therefore, we had to come up with simple models which can make the analysis of diode circuits extremely simple. So one of the first models that we discussed was called as an ideal diode model, wherein the forward, whenever the diode is conducting current, we assume that the forward voltage of the diode is 0, and it behaves like a short circuit. But this is a diode; it can only carry current in one direction. Okay, so in this case, if I use an ideal diode model, it shows that since the diode voltage is always 0 for any value of current, the power dissipated across the diode is 0. The DC power dissipated across the diode is 0. Okay, so but in practice, we have to assume, in any practical circuit. So for example, when I have a simple circuit like this, I'm going to feed in some VDC, which is say greater than V gamma. So which is greater than V gamma. So then the voltage drop across the resistor is going to be VDC minus V gamma, which is less than the input. So therefore, this model actually models the loss in power in the diode as well. Okay, if I use an ideal diode model, the entire voltage will appear across the resistor, and the entire power that is delivered by this voltage source will be dissipated across the resistor itself. But if I use a model wherein I'm going to assume that the diode actually has a finite cut-in voltage, meaning again I've already defined what a cut-in voltage is. I said that in the last class, the diode a cut-in voltage is a parameter that is normally derived normally derived by the circuit designer based on the operating currents, range of the operating currents. So you normally from the the IV graph of your diode, you can extrapolate the line and see the point where it intersects the x-axis. Okay, and that point will normally be your cut-in voltage. So we'll have to see what is the peak current or the max current that you're going to operate. From that graph, you can actually find the value of V gamma, and we said that it will vary if your currents are going to vary. Okay, for much higher. For example, if the Imax is 10 times or 20 times higher or 100 times higher, then V gamma will also have it will not have a proportionally larger change, but small changes. Okay, so we discussed about how to model the diode as a voltage source. And we also discussed that when we go for circuits where we apply sinusoidal inputs or varying inputs, not just DC or constant inputs, but where you're going to apply sinusoidal inputs, we also have to capture the effect of the diode, okay, on the output voltage. Sometimes I said that when the diode doesn't behave like a perfect rectifier, there is a small for example, in this circuit, I had taken a different circuit in the last lecture. I had taken a circuit where there was resistor and a diode. So for a positive, whenever the sine wave is assuming this is an ideal diode, so whenever the voltage was greater than 0, the diode was short circuit. It was just behaved like a short circuit, and we said that the characteristics was something like this. Okay, but in reality, ideally, and we also said in the presence of a finite V gamma, the characteristics is going to be something like this. So it will be following the input until V input is less than V gamma, and after that it's going to saturate to a value of V gamma. Okay, and we said that when you feed a sine wave to this system, you are going to get a clipped waveform. It was called as a clipper, where the negative cycle is fully passed but the positive cycle is clipped. Okay, and the value is V gamma, and he said that there is a small it doesn't perfectly flatten out like this, but it had a small sinusoidal variation, and that could be explained by modeling a finite on-state resistance for the diode. There is one other reason why we model on-state resistance for the diode, and that is to model the AC power dissipated across the diode. So for example, let's take a circuit like this, and I'm going to apply a sine wave a small sine wave riding on top of a DC signal such that this overall signal, this is your input signal, is always greater than V gamma. So in that case, I can simply replace this circuit with, so V gamma, it's a voltage source, it's just a voltage source and a resistor shown here. So for this signal, I can split this signal as an AC signal and a DC signal. When you apply an AC signal, this model of an ideal DC source says us that there is zero AC power dissipated across the voltage source. The AC power is entirely dissipated across the resistor itself. That's what this model tells us. So just to refresh your memory, what is AC power? And the difference is that if I have a sinusoidal signal, V cos omega naught t plus phi fed as an input to a, or let me just assume with a zero phase, omega naught phi as a voltage input to any two terminal device. And if you know that the current is actually going to be IP cos of omega naught t plus phi, again we know this phi can be plus or minus pi by 2 depending upon inductor or capacitor. For resistor the phi will be 0, both the current and voltage will be in phase. Then we find the definition of power in that case for periodic signals we can define average power. So that is the power dissipated in a single cycle. That turns out to be equal to Vp Ip by 2 into cos phi. For a resistor, for a purely resistive load, phi is 0 because current and voltage will be in phase. So this value will reduce to Vp Ip by 2 for a resistor. And the term, we can also define this as Vp by root 2 and Ip by root 2, and this term is called Vrms, the RMS voltage, and IRMS. So we can compare this to, for a DC input, we are going to have VDC into IDC. Okay, so for AC signal we define two terms called RMS. For a AC voltage we define Vrms, and similarly we can define IRMS for a current source. RMS is nothing but the root mean squared value. So you square the signal, compute the average in a single cycle for a periodic signal and take root of this. So this is going to be your RMS value. For a DC signal, the RMS value will be equal to the DC value itself. So because your DC is going to be constant, so let's say I'm going to write it as VDC square. If you integrate this, you are going to get T, 1 by T will cancel out and you will be left with VDC itself. For a DC signal, Vrms will be equal to DC itself. For any sinusoid of finite frequency, the RMS value is going to be V peak by root 2. Okay. So this is the AC power. This term is what we call as AC power. For a diode, since we are going to model it as a constant voltage source, so in this circuit, even though there is a sinusoidal AC current, IP is a sinusoidal current, I am going to call it cos omega t plus phi, is flowing in across the diode. If I compute the power, that is the product of this voltage is V gamma, so I am going to have V gamma into IP cos omega t plus phi. Okay, phi can be 0 here, I am just assuming some finite phi here, and then compute the integral of this over a single cycle. Then we know that if I am going to integrate a sinusoid for one single cycle, the average value will be 0. So this says that the average power dissipated across the diode is 0, meaning the sinusoidal power dissipated is 0. There is only DC power. Okay. So then to capture AC power, to also capture the effect of power loss for sinusoidal signals, we have to model the on-state resistance. So in case of R-on, all we said that was, now the model is going to be somewhat like this. So of course we are going to start at V gamma, but instead of it going as a straight line, as a line with infinite slope, it's going to be a line with a finite slope, and this was called 1 by R-on. And in the last class I think I made a small mistake while defining R-on. I've defined R-on correctly, but when I wrote it as this, so R-on is nothing but dou I by dou V, the whole inverse, and this value should be estimated at I equal to the quiescent diode current. Okay, so essentially what we are doing in this example is that we are estimating the on resistance of a diode at a single point. So if you see the IV characteristics of a diode, as your current varies, okay, the slope of the signal also keeps varying. It's an exponential curve, so the slope in fact keeps increasing as one increases the voltage, okay, or the current. The slope keeps increasing. We can very easily show that the slope, which is dou I by dou V, depends upon IDQ upon VT, where I'm assuming eta is 1. Okay, in this case it's simply IDQ upon VT. It's ideally eta VT, but for an ideal, when I say the ideal diode, this is from the physics point of view. For the ideal models for a diode that we use, the eta value is 1. Okay, for silicon it's going to be 2. We will get IDQ by IVT. So what this equation tells us is that as I change my operating current, if let's say I double my operating current, then the on resistance should become half, or rather dou I by dou V doubles. So your on resistance R on from this equation is 1 by this. So if I double my current, the on resistance should reduce by a factor of half. So that's evident because on an exponential curve, when I'm going to move to a higher value of current, the slope naturally increases. It's going to increase faster and faster. Okay, so when I'm going to use a straight line, where that is a linear line to model a diode resistance model, what is going to happen is that, of course, the model will work for a small range, but it's an exponentially increasing function. Okay, so eventually the model and the actual diode equation which we use to model and the actual diode equation, the error between the two will start diverging. And I think I've discussed this in the last class. This is a linear equation which is of the form x. Okay, I'll just assume y equal to f of x, kind of a function. You have an exponential function which is increasing exponentially, and if you divide this by x, okay, or let me define it this way, x by e power x, this function in the limit as x tends to infinity will always tend to 0. Okay, in fact this is true even for x power n, any finite value of n, any polynomial or in x, when you divide it by an exponential function, eventually as x tends to infinity, this value is going to tend to 0. What it means is that your exponential function is eventually going to increase much faster compared to any polynomial of finite degree. Okay, so we can intuitively, very easily prove this result using L'Hospital's rule. Okay, because e power x contains an infinite polynomial of infinite order. It's a infinite series, 1 plus x by 1 factorial and so on plus x power n by n factorial. The series keeps it's an infinite series. So therefore, when you take the ratio of this, eventually this function will blow up to infinity much faster than this function x power n. So the limit as x tends to infinity will tend to 0. So therefore, what I'm trying to say by this is that this model is never going to be accurate if you're looking for extreme accuracy. This is going to be accurate for extremely small variations around this point. Okay, but if you're looking for better accuracy, then we have to change the model. Okay, so now I'll just come back because we are discussing about the linear model for a diode. The main point for this discussion is that if you want to model power loss for AC signals, then you have to model the on-state resistance. Okay, that is one of the main motivations, because one of the popular applications of diode circuits is when you are going to use diodes in bridge circuits, meaning when in circuits where you have to convert an AC signal to a DC signal. There we are interested in the term called efficiency. How efficiently can you convert it into a DC signal? And anything, the diode is actually it's practically it's used in almost all of this AC to DC conversion circuits, and some amount of power is actually, the AC power is also lost in the diode. Okay, to capture that we need to model the on-state resistance, because if I'm going to have a linear model, then as I said, the model for the diode in this case is going to be, we'll first model this as an ideal diode with 0 cut-in voltage, and then we are going to add a voltage source of value equal to the cut-in voltage and a resistor of value R on, and the value of R on is given by VT upon IDQ. The last class I wrote this as an inverse by mistake. I just noticed it a few moments ago, so that's why this is the exact expression. So this is simply dou I by dou V whole inverse evaluated at the quiescent diode current. Okay. Again, this model is valid if your voltage variations across the diode is small. So since it is of this type, now when I have some variations in the voltage, there will be some variations in the current as well. So there will, if you, when you have a sinusoidal AC voltage variations across the diode, you are also going to have a sinusoidal variation in the current. So that effect is captured by Oron. So two main reasons. One is to actually better approximate what happens in reality, and second thing is to also model the AC power loss in a diode. So on-state resistance is useful in that. So now in the last class, when I've already discussed this, I just wanted to give a motivation behind why do we go for Oron. In the last class, when I just finished off the lecture, I just discontinued at the point where we were talking about more and more accurate diode models. So I'll continue with that. So I said one of the problems with modeling the diode for a larger range of currents is that the slope of the diode equation keeps changing. It's variable slope. As you increase the voltage or the current, the slope also keeps changing. So we need a model which can actually capture this effect of changing slope. Okay. And again, our model should not contain anything other than resistors and voltage sources. Okay. And of course, there is an ideal diode. Ideal diode is zero cut-in voltage diode. We can use that in the model and some voltage sources and resistors. And then we should be able to somehow capture the effect of varying on-state resistance as your currents increase. One way is you can see that, for example, if I can somehow model this equation, maybe let me use a different. So in this range, so I can have a Battle model in this range with a certain slope, and then in a different range, say I'm going to call this as V gamma 1 and V gamma 2. After this range, I want the slope of this line to change, slightly increase. So what does this mean? If slope is increasing, Ron is reducing. So I need to have a model. Let's say I'm interested in modeling it in this entire region. And I can actually better approximate it by two piecewise linear curves. Then how do we model it is by using an approximation like this. So first I'll consider an ideal diode and with a value of V gamma 1, Ron 1, and I'll put another diode model Ron 2. So essentially what I'm doing here is that, so I'm adding two diode models. So this is V gamma 1, the other model it is V gamma 2. Now when you add these two models, I'm going to get a composite curve. So which is actually first it's going to be constant till this point, and then it's going to raise with this slope. The moment it hits V gamma, then you have to add this plus this, so that obviously the slope is going to increase. So it's going to increase like this. Now when I use a diode, actual graph of a diode, it's going to look like this. So previously when I was using this model, using a single resistor, the error here was increasing, but now using this two diode and two resistor model, I could reduce the error in this region. Okay, that is one of the main motivations for going for this. So by using a model like this is an ideal diode with zero cut-in voltage. I'm going to put that in series with a cut-in voltage and a finite Ron. So now if we'll analyze this circuit itself. What happens in this circuit is for V in, when your input voltage across the diode, I'm going to call it as V as the input voltage across the diode. So let me redraw the model here. So this is a diode with a finite cut-in voltage, and I want to model having a diode having variable slope. All I can do is I can take two diodes with different cut-in voltages and on-state resistances and put them in parallel. I'm going to call this 1 and 2. Now if V is the voltage across this diode, I can very easily show that for 0 less than or for V less than V gamma 1, your diode, both the diodes are going to be off. So here it is assumed that V gamma 2 is greater than V gamma 1. Now when your voltage is greater than V gamma 1 but less than V gamma 2, only one path will be on. The current will be flowing in only one path, and at that point the on state resistance is going to be simply R on 1. It's going to be simply R on 1. Now when your input voltage is greater than V gamma 2, then both the paths will be on. In that case, the on resistance is going to be R on 1 parallel R on 2. Okay, so your resistance actually reduces. So that is nothing but an IV graph. The slope has actually increased. So that way we are able to model the variable slope of a nonlinear characteristic of a diode by using this composite model. So if you want to increase more, if you want to get even more and more accurate slopes for larger ranges of voltages and currents, you can keep adding more and more diodes in parallel, such models in parallel. So V gamma 1, V gamma 2, and then V gamma 3, and so on. I'm going to call it as R1, R2, and R3. Okay, so this way I can keep increasing the accuracy of the diode models by using more voltage sources and ideal diode models in this manner. Okay, so with this I've completed the models of the diodes, and I think in the next lecture I'll start discussing about problems on diode circuits just using the diode models. So I'll stop this lecture at this point. So ideally this lecture is supposed to be a more like a small, like it's more like an appendix to the previous lecture, because I think I had to discontinue the last lecture, and towards the end of the lecture I just wanted to finish off this diode models with variable slope. That was the only purpose of this lecture, but I also felt I made a few mistakes here and there. I wanted to correct it in this lecture. Okay, I'll stop at this point.